Okay, so let's get started. Where are others?
So we can wait few more minutes,
Hmm? Yeah, so let's,
maybe around 1 2 minutes.
yeah, okay. Who else is supposed to join? Ayush, right? So he wanted. Okay, so this is the slide that I shared in the first class. Okay, I don't know if I shared this, but this is. I thought I'll continue with this particular as whatever scheme. Okay, basically you'll have a slide okay. Is that fine, everyone?
Yes, sir.
Okay, so I can share that thing with you all. So I'll share the slide with you all today. Okay, immediately after the class. Okay, so let's get started. A gentle reminder on next week's quiz. So be prepared. So it'll be, as mentioned, it'll be on the it's a collaboration mode based exams, wherein each question, some of you will collaborate in answer. Okay. Okay, so let's get started. So in the last class, we looked at a few things. For example, we saw that if you take a non-negative random variable, and if you look at expected value of min of x comma n, as n goes to infinity, this expectation goes to expected value of x. And then subsequently, we proved a very important theorem called what? Hmm?
Monotone convergence.
Monotone
Convergence
convergence
theorem.
theorem, right? Then we looked at, did we stop here, or did we look at anything else after this? No? Excuse me. Did we, so monotone convergence theorem is something that we looked at, and then we didn't look at anything else, right? So, okay, fine. So, what is monotone convergence theorem? So essentially you have positive or non-negative random variable, which is monotone, meaning x1 less than or equal to x2 and so on. And limit or xn converges to x almost surely, then I can interchange limit and expectation or integral, right? Xn would be expected value of limit for all in limit n tending to infinity xn, right? This is what we what MCT essentially says. Okay, so we will look at another very important theorem. We'll look at two important theorem along these lines. The first one is not really a theorem, but it's called Fachos lemma. Okay, so if you take a sequence of random variable non-negative, okay, then okay, so this is something that I haven't taught you, so let me just spend some time on this. Limit of as n goes to infinity, expected value of xn, okay, is greater than or equal to expected value of lim in of xn. Okay, how many of you know what lim inf is? Hmm? Okay, how many of you don't know what lim inf is?
Me, sir.
Arvind, okay. Jayant, what about Nitish? I know, okay, you don't know. Sumit,
Yes, sir. I know.
okay, otherwise you wouldn't have been here, okay. So if you are from math background, you don't know, then I wouldn't have taken you. So, okay, fine. Let's look at what is lim inf, okay. So let's I'll write it as a discussion. Okay. So let's look at this sequence 1 minus 1, 1 minus 1, and so on. So this is a sequence of numbers, right? Will it converge? You now know a very rigorous epsilon delta definition of a limit, right? Essentially, it says that an converges to a if you take any room epsilon around a, then there exists a stage beyond which the sequence will enter that room and stay there forever, right? That's what it essentially means. Okay, now what can you say about this sequence? Will it converge?
No, sir.
No. Nitish, it doesn't, right? Because if you say that, it can either converge to 1 or minus 1, right? Because it's alternating between 1 and minus 1. If you take, for example, 1 as the limit, and if you put an epsilon, let's say 0.1 room around it, then obviously at some point it will be exactly 1. The difference is 0. It enters this room and it goes out of the room. Enters this room, goes out of this room. So it will never enter this room, epsilon room, and stay there forever. So this sequence does not converge, right? But if you look at this seemed to go to what? It seemed to go to 1 and it seemed to go to minus 1, right? Something like this. It sort of oscillates between the two. Now, supposing, let's say I want to have some, so think of this as for those who are in communications, for example, think of this as your power. Okay, so you boost the power, reduce the power, boost, reduce, and so on at different stages. And then you want to know what is the worst sort of power that you are using in the long run, right? Or asymptotically, what is it that you will observe, right? Or what is the best power that you are going to use, and so on. So one way to handle that is you take this sequence, okay? What you do is you take the supremum of this. So take the entire thing, supremum. So what is it that I'll get? Of course, 1, right? Now I'll start from the second stage and take supremum. Again, I'll get 1, and so on, okay? So this essentially what you end up getting is a sequence 1, 1, 1, 1, etc. Right? Is that fine? Right? Okay. So this sequence obviously converges to 1, which it has already converged here in the first place itself. So it goes to 1, right? So I can define my my limb soup, okay, of a sequence as the supremum of all the numbers. You'll get a number, then you leave out the first one, take the supremum of the remaining, you get another number, leave out the first two, and then take supremum of all the remaining, and so on. You can get a sequence of numbers. Look at the limit of that. Well, limit exists because if you take supremum of lesser numbers, that is a monotonically decreasing function. So obviously it should converge, right? It may converge to infinity, but that's okay. It will converge to something. Okay. Well, I can't say it converges to infinity, but it may diverge to infinity, but that's okay, right? So now, how do you formally define this definition? Let an be any sequence, okay? Then lim soup n10 into infinity an is defined as, what I will do is I will take this ak, right, and I will take the supremum over all k greater than or equal to, let's say, L. Okay, for example, L equal to 1, then it's the entire sequence. L equal to 2, you start from the second one, third one, and so on. You get a sequence. So this itself is a sequence. Okay, this is a sequence. Now I'll take the infimum over all this L. Okay, for example, in this case, if you get 1, 1, 1, 1, infimum of that is 1, right? That's how I define. Okay, or I can take the limit also, doesn't matter. And similarly, lim inf n tending to infinity, a n is defined as supremum over all L, infimum over all k greater than or equal to L, a k. Okay. So all that I do here is I take the infimum of all the numbers in the sequence, leave out the first one, take the infimum, leave out the second one also, take the infimum, and so on. You get a sequence, you take the supremum of that, that is your lim inf. Okay. So of course, this I can, take the limit over all L tending to infinity, right? And similarly here I can take limit L tending to infinity. Is this okay? Let me give you an example. Let's say 0 minus, sorry, 1.8 to 1, 0, 1.8, 2, and so on. What is the lim sup of this? Can Praveen tell me what is the lim sup of this? Yes? Praveen, are you there?
Yes, sir. Yes, sir.
Yeah. What is the first thing that I have to do?
Take the supremum of the entire sequence.
Entire
Is
thing.
it
So what is the
yeah,
supremum?
2?
2, right? Then what should I do?
Then leave out first thing, and
Yeah,
again it
take
will be 2.
2, right?
2
And
entire
so
thing.
on. And then take, you get a sequence, right? The
Yes, sir.
sequence.
Limit
Limit. What is the limit?
2.
2, right? 2 is the lim sup, right? Or it should take the infimum of this sequence, 2, 2, 2, 2. So you get 2, right? Is this fine? Okay. Fine, right?
Yes, sir.
Okay. Okay. So I can write another, maybe another sequence. So for example, 1, 1 by 2, okay. Then 1, 1 by 2, 1 by 3, then 1, 1 by 2, 1 by 3, 1 by 4, and so on. Okay. Now, what do you think is the lim inf of this? Can somebody else tell me? Maybe Jayant or Rishabh, can you tell me? Lim sup of this?
Sir,
Rishabh,
actually, I
are you
missed
there?
the first 10 minutes.
Oh, you didn't. Oh, okay. No
Sir,
problem.
sorry, I fell
So,
asleep. Yeah, sorry.
we were looking at the notion of lim inf and lim supremum. Okay. So, lim sup, what you do is you take a sequence, you take the supremum of that. For example, here the sequence is 1 minus 1, 1 minus 1, which doesn't converge, it diverges, right? You take the supremum of that. Supremum is 1, right? You lower out the first term and then take the supremum of that. It's 1, and so on. You get a sequence of 1 and you take the limit of that. That is 1. Or you take the infimum of that. It's 1, right? So one way of defining that is you take supremum over all k greater than or equal to L of ak. Okay, for example, L equal to 1, it's the entire sequence. L equal to 2, you start from the second one. L equal to 3, start from third one, and so on. You get a sequence and take the infimum of that over all L, or you take the limit. And similarly for this. So lim inf, what do? You do exactly opposite. Okay, so what is the lim inf of this? You take, instead of supremum, you take infimum. Infimum is -1, right? Then again, instead of supremum, you take infimum, which is -1. So you get a sequence of -1, -1, -1, and so on, which converges to -1. So -1 is the lim inf. Okay. Similarly, what is the lim inf of this? Let's look at this. First thing is you have to take infimum of this. What do you think is the infimum of this? Can somebody tell me what is the infimum of this sequence?
Sorry, 1 about n tends to infinity.
So that is no. See, remember 1 comma half comma 1 half 1 by 3, 1 half 1 by 3, 1 by 4, 1 half 1 by 3, 1 by 4, 1 by 5, and so on. That's the sequence. So infimum is obviously, it'll be 0, right? If you start from the entire thing. If you start from the second also, it is 0. If you start from third also, it's 0. So essentially, you get a sequence of zeros, then you take the limit or take the supremum. So it is 0. So lim inf is 0. What is lim sup? It will be 1, right? So this will be 1. Okay. And then again, here also it will be 1 and so on, and take the infimum. So 0 and 1, right? This is the worst. So essentially 0 and 1 are the lim inf and lim sup. These are also called as limit points. Okay. And because, for
So
example,
can
here
you tell
also,
once again, sir, lim inf is 0. Can you?
so if you look at the entire sequence, what is the minimum or the infimum? 0, right?
Yes, sir. Well, it tends to 0. That's why, right?
No, it is 0. Infimum is 0, right? By definition. Not by definition. So you can prove that it's 0, right? Because if you take any other number, for example, you take epsilon to be your infimum, then I can argue out saying that epsilon is not the infimum, right? Why? Because if you say epsilon is the infimum, then
We can
I can
find
choose an
smaller
n such
than
that 1
epsilon.
by n is smaller than epsilon, or n is greater than 1 by epsilon seal, right?
Yes,
Which
yes.
is always possible, right? Because down in the sequence, there is a huge 1 by 2, 1 by 3, and so on, which is 0. So it is 0, right? Do you agree?
Hello, sir.
Yes.
Sir, if it is minimum, it's not 0, right? It's tending to 0.
Yes. Minimum, you cannot say it is 0 because, minimum doesn't exist here. Okay. 1 and 0, right? So these are called limit points. Similarly here, 1 minus 1. So these are also called limit points. Okay. Is that fine? So you have, what lim sup and lim inf are. Okay. Let's move on. So let's look at this thing, right? So whatever we wanted to prove, right? So it says lim inf of the expected value of the sequence is greater than or equal to this thing. Okay. So now let me write lim inf as the limits, right? So let's look at this. Okay, let's look at the proof of Facho. You look at lim inf of xn, right? So this is nothing but I can write this as limit n tending to infinity, right? Since it is lim inf, I can take k greater than or equal to n. Okay, so this is what it is. Do you agree? Do you agree? Do you agree, everyone?
Yes, sir. Yes, sir.
Right? Okay. So now, what can you say about this? This is some sequence an. Do you agree?
Yes, sir.
Because I pick different n, I get different numbers, so it's a sequence. What can you say about the sequence? For example, a1 is what? You are looking at the infimum over all the numbers starting from 1, right? What is
Increasing,
a2?
sir.
Yeah, increasing, right? So an is increasing. Okay, fine, it is increasing. Okay, now so it increases to what? Limit, right? That's what it is, because you're taking the limit. So increases to
Hello, sir.
limit.
Hello.
Yes.
Sir, is it because xn is increasing?
Yes. No, xn is not increasing, right? Xn, I'm not saying xn will be a sequence of positive random variables. That's all I mentioned, right?
No.
See, xn greater than almost surely. That's all. Positive, non-negative random variable. I didn't say it's increasing. Can you tell me why this is increasing, an?
Sir, it is just by the definition only, sir. The way we have defined.
Infimum of a larger set is always smaller
Yes.
than the smaller set, right? What is infimum of 1, 2, 3? 1. What is infimum of, let's say, 2, 3? 2. What is the best case scenario? One infimum of 1, 2, 1. So you'll get back 1, but it's always increasing, right? So this is the limit. Do you agree? Do you agree?
Yes, sir.
Okay. So therefore, I can write xn is greater than or equal to infimum over all, let's say, k greater than or equal to n xk. Do you agree? You agree with this? Why? I'm taking infimum. If xn is the smallest, then I would have taken xn. Infimum over all k greater than or equal to n, xk would be xn. Otherwise, I will pick something smaller than xn. So therefore, xn is always greater than or equal to this. So this implies expected value of xn greater than or equal to expected value of infimum over all k greater than or equal to xk. Do you agree with this? You agree with this? This is true for every n, right?
Yes, sir.
Any question? This follows from the usual stuff, right? Okay. Now, what can you say about this sequence? This sequence is increasing. Do you agree? Right? Therefore, expected value of this also increases, right? Expected. So if I call this as sequence yn, then expected value of yn is smaller than or equal to expected value of y2 smaller than or equal to, and so on. So this whole thing is increasing, right? And this is true for every n. So I can take, for example, infimum over all n expected value of xn. So basically, I can look at n greater than or equal to some l. Okay. If I take infimum over all that is greater than or equal to, this is true for every n, right? So you pick any n, that is true, right? Do you agree?
Yes, sir.
Okay. So I can essentially write this as infimum over all n greater than or equal to l. Okay. Expected value of yn, because yn is this. Now, this is true for every L, right? Therefore, this implies I can take the limit. Okay, limit L tending to infinity, infimum over all n greater than or equal to L, expected value of xn is greater than or equal to limit L tending to infinity, infimum over all n greater than or equal to L, expected value of yn. Okay. So what is this? This is nothing but lim-inf, right? Lim-inf n tending to infinity, expected value of xn. Okay, this is fine. This is also lim-inf, right? So lim-inf n tending to infinity, expected value of yn. This is what it is. But expected value of yn is increasing, right? If you take lim-inf of an increasing function, you get the limit, right? Same as the limit, right? Check that. Okay, so limit of an increasing function is always expected. But what is this? Yn, if you look at this, yn is increasing, right? This is also increasing. Do you agree? It's non-negative and it is increasing, right? Yn is non-negative and increasing. Now what do? What will be the next step?
Sir, monotone
Apply
convergence theorem,
MCT.
sir.
Yeah, apply MCT, right?
MCT.
So, good. So apply MCT and exchange the limit and integration. So it will be limit n tending to infinity yn. Infimum over all k greater than or equal to n xk, right? Sorry, not xk. Yeah, it's correct, xk, right? So this is nothing but expected value of liminf of xk, k got to infinity. Done. QED, right? Nice, right? So this is a nice application of Fatuous lemma. I should have saved this. Okay. Is this fine? Okay. So the
Yes.
next one that we are going to look at, yes, question?
No, sir.
Okay. So the next one is a very important one, perhaps the last one, which is the dominated convergence theorem. Okay. So what is this saying? So now I won't prove this. I'll leave proof as an exercise. So you take two random variables, so one sequence and one random variable xn. Okay, so you have x and xn, the random variables. Okay. Suppose there is a random variable such that xn absolute value is less than or equal to y almost surely for all n. Okay, this is one thing that we have. Okay, and xn converges to x almost surely. Okay, this is also something that we have. Okay, the third thing that we have is expected value of y is less than infinity. Okay, then limit n tending to infinity expected value of yn or xn is equal to expected value of x. Expected value of x is basically, it says you can interchange the limit and integration without any problem. Okay, this is called the dominated convergence theorem. So what it's saying is, essentially it's saying if xn converges to x almost surely, and if you have a y, a random variable y which is larger than xn but with the expected value of y being finite, right? So it's called dominated. It's dominated by another random variable y such that expected value of y is less than infinity. Then I can interchange the limit and integration. Okay, is this fine, everyone?
Yes, sir.
Okay, it's fine, right? So it uses Fatuous lemma, and essentially the way you prove this is you prove two things. Okay, limit of this is less than or equal to this, limit of this. So I can instead of limit, I can take liminf and limsup. Okay, so there is one more note. If liminf an equal to limsup an, then an converges to a, which is nothing but limsup of an or liminf of an. Okay, that means if the both limsup and liminf are same, then we say that an converges, and it converges to the limit a, which is given by limsup or liminf. Okay, so basically you show that liminf is less than or equal to this, limsup is less than or equal to this. Basically you have to show that liminf of an is greater than or equal to this, limsup of this is greater than or equal to liminf, therefore both are equal and the equality is expected value of x. That's the idea of the proof. Okay, so there is one more small thing. This is dominated convergence theorem. There is something known as bounded convergence theorem. Essentially it says that if xn is less than or equal to some constant m, then you can interchange. Okay, so basically this y if y equal to m, okay, belonging to R plus, then DCT is called bounded convergence theorem. That's all. Okay, this is trivial thing. Is this okay?
Hello, sir.
Yes.
So then, when you say a random variable is less than another random variable, we say it's like pointwise less than.
It's almost sure, right? So the outcomes for which xn of omega absolute value is greater than y of omega has zero probability.
Zero probability.
Yeah, that's what it means. Okay, right? Is that fine?
Yes, sir.
Okay. So this is
Hello,
something
sir.
that is
BCT.
quite useful. Yes. Yes.
One time again repeat, sir. BCT.
You want me to repeat?
BCT bounded.
So if you instead of a random variable y, you assume a number, okay, for example 3 or 4, whatever, some m, right? Then m finite, then this theorem is called BCT, bounded convergence theorem. Okay, nothing much.
Hello, sir.
Who was this? Nitesh? Yeah.
Does that
Yes,
imply x is also less than m?
yes, right. So if y is m, I mean, instead of a random variable, you take a number, then of course xn is also less than or equal to
x.
Oh, x you are asking. The true, right?
Yeah, okay.
True. Yes. How do you prove that? Okay, so maybe I'll take that. See, you are saying xn is less than or equal to, let's say, y. Okay, some random variable y. Okay, and xn converges to x almost surely. Question is xn, sorry, is y is x less than or equal to y? Almost surely. Question, right? You agree? So now what is it saying? So if xn converges to x almost surely, so so the question would be probability of x less than or equal to y is 1. Question. That's what you're asking, right?
Yes.
Okay. So now I can do the following, right? So since xn converges to x almost surely, there exists n such that xn, so if I look at capital Xn, right? If you look at the difference between the two, okay, it will be small. I can always do that, right? This is true for every epsilon greater than. Give me any epsilon, I can ensure that this happens with probability 1, right? So now probability of x less than or equal to y, I can write this as x minus xn less than epsilon plus probability of x less than or equal to y and x minus xn greater than or equal to epsilon, right? So now so I have to okay, so now okay, so let me prove the other way. Okay, so I will prove greater than or equal to 0. Okay, so instead of that I'll take greater than y. Okay, so what does this mean? So if x minus xn is less than epsilon, then xn is greater than x minus epsilon, right? Or sorry, x is less than xn plus epsilon, right? And this one will tell me, well, we don't care about this. Okay, so this will tell me x is less than xn plus epsilon. Now this will be, so if I replace x by something larger, right, the probability will always be larger, right? So xn plus epsilon is greater than y, and I leave out this, so it is again an upper bound. So again what I will do is xn minus xn greater than or equal to epsilon, right? Do you agree? Now what is this? This is probability of xn greater than y minus epsilon, right? Plus probability of this thing. Now epsilon and n are arbitrary, right? So I can take n to infinity. So this, what happens to this? And I can make epsilon arbitrarily small, right? Right. So this is for every epsilon greater than 0, right? So this will be probability of, in the limit it becomes x, right? So, or I can pick an epsilon n large enough so that this is greater than epsilon, which is actually 0, right? Because xn is always less than or equal to epsilon. And similarly, this also goes down to 0. Okay. So that's the idea of the proof. Let's, I think I don't want to waste more time on this. Okay, maybe I think we need some refinement here to the proof. Can one of you or all of you discuss about this and come up with the proper proof? Okay, I think you got the idea, right? The gist of it. Yeah. Okay, so I think we will move on. So I think this is what I wanted to say about the probability part. Let's move on to stochastic process. So this is chapter 2 of the book. Especially we look at Poisson or the Poisson processes. Okay. So now, so let's look at an example. So let's say people are arriving at a counter. Okay. So now this is my time axis. Okay. People are arriving at a counter at random times. Okay. So for example, the first person arrives at S1, the second person arrives at S2, the third person arrives at S3, fourth person arrives at S4, and so on. Okay. Right. So what is ST in general? Sorry, S4. Sorry, SN. Time at which? Can somebody tell me what this is? The nth arrival happens. Okay. It could be, for example, if you are looking at a queue, then it's the time at which the nth person arrives at the queue or arrives at the counter, right? Or if you are looking at packets, it's the time at which the nth packet arrive at a router, your Wi-Fi router, right? Or you can also think of it as departures, right? This is the time at which the nth person leave the counter. Okay? It doesn't matter, right? So you can look at it in either way. Okay. Okay. So this SIs or SNs are called arrival process. Okay. Is that fine?
These are random, right? It can leave or
These
any
are
time.
random. Yes. These are randoms. Okay. So let's formally define this. Well, I want to abstract this out. I don't want to say arrival and all that. So, I don't want to attach this to some examples. I want to generalize this. So an arrival process is a sequence of increasing random variable. Okay. 0 less than S1 less than S2 and so on. Okay. What does this mean? This means that Si plus 1 minus Si is greater than 0 almost surely. That's what it means. Okay. Is that fine? See, it should be strictly greater than 0. Okay. The probability that this is equal to 0 is 0. That means in this example, no two people arrive at the queue at the same time. Okay. That means this SIs are continuous. Okay, it's not discrete. If it is discrete, there is a chance that you can arrive at the same time. It's continuous, right? So the probability of two people arriving at the queue at the same time is 0. Okay, so this is called an arrival process. Okay, so now how do you describe this? Well, it's very complicated process, right? So S1, S2 is the time instant at which people arrive. So instead of describing this process in terms of the arrival process, there is an alternate description. So for example, let's say this is your time. Okay. Is Ayush there today? No. Okay. So this is your time, and let's say the first one arrives here. Let me use a different color. The first one arrives here, the second one arrives here, third one arrives here, fourth one arrives here, fifth one arrives here, sixth one, and so on. Okay. Now, instead of describing this as S1, S2, S3, and so on, I'll describe it in terms of the inter-arrival times. So I will call this as X1. That is the time that it took for the first person to arrive at the queue. This is the inter-arrival, right? This is the time that it took for the second person to arrive at the queue after first person arrived. Okay. This is X3. This is X4. This is X5. And so on. Okay. Is that fine? Is that fine? So
Yes, sir.
essentially Xn is what? Inter-arrival time between what and what? Between n minus 1th arrival and nth arrival. So mathematically, how do you write this? Well, in terms of SIs, it's Sn minus Sn minus 1. Do you agree? This
Yes,
is how
sir.
I can write. Do you agree? So this is for all n greater than or equal to 1. So this is how I can write. Okay. So now I can
Sir,
also write.
SN is like the total number of persons arrives at a time t is equal to n, sir. No.
No. Sn is the time at which the nth person arrives.
Means SN is your time, no, sir.
Time, yeah. Sn, for example, S1 is the time at which the first person arrived at the queue. S2 is the time instant at which the second person arrived at the queue. This is your time, right? This axis.
Okay.
Just remember this picture. Okay. On the other hand, I can also write Sn as what? Sn is the time instant at which the nth person arrived, right? So this is nothing but, for example, this is your what? S5, right? S5 is nothing but X1 plus X2 plus X3 plus X4 plus X5, right? So that means if I add Xi's, I should get Sn. Do you agree?
Yes, sir.
Yes.
This is true for n greater than 1, right? For all n greater than 1. Okay. So typically, people describe this arrival process through Xi's, that is the inter-arrival time. Okay, is that fine? Everyone understood what this is?
Yes, sir.
Okay. There is one more way of looking at this, right? I can essentially count the number of people coming into the queue, right, in some epoch or an interval, right? In other words, I can describe it in terms of what is known as a counting process. Okay, so what is a counting process? So let's look at it in terms of counting process as well. Okay, so what is a counting process? Before that, let me just denote it by n of t. So what is n of t? The number of people arrived at the queue until time t, right? So number of arrivals until time t. Okay, you understood, right? For example, let's look at this example, or maybe this example. Okay, so if you look at t to be somewhere here, okay, t to be this one, okay. What is n of t here? Can somebody tell me?
3.
Then,
3.
3, sir.
1, 2, 3. Right? This is 3. Yes. Right? This is n of t. Is that fine? So n of t, so for example, if you look at this process, right, n of t, t greater than 0, is in fact an uncountably infinite family of random variables, right? Is an uncountably, well, I can say uncountable, that's enough, because infinite is uncountable family of random variables. So it's very difficult to describe this, right? So you need to, how do you describe a random variable? It's in terms of distributions, right? PDF or PMF or something. How do you describe two random variables? Joint distribution. How do you describe countable random variables? Joint distribution. But if you have a continuous process, very hard, right? So it's not so easy, not so straightforward. Okay? Is that fine?
Yes, sir.
Okay. So now let's look at in terms of events. Okay, so suppose I say Sn is less than or equal to t. What do you mean by that? What do you mean by that?
There are n people has arrived till the time t.
So Sn is the time instant at which nth person arrived. So that this particular event says the time at which the nth person arrived is less than or equal to t. That means within time t, so this is your t, 0 to t, there were n or more arrivals. N or more. Okay, that's what it says. Okay, now let's also write this. N of t, okay, is greater than or equal to n. What is this saying? N of t is the counting process, right? It's the number of arrivals until time t. So this says that this event says that the number of arrivals until time t is more than or equal to t, more than or equal to n, right? It's saying more than n people arrived at the counter at time t, more than. This also says the same thing. So both are equal. Do you agree? Is this fine?
Sir, can you elaborate this? Sn is less than t. Once more,
So
sir.
what do you mean by Sn less than or equal to 1? Can you tell me what is Sn less than or equal to 1? What is Sn?
Sn is, sir, nth arrival, sir.
No,
Time
it's
of
not.
nth.
Correct. Time of nth arrival.
Nth arrival.
Right?
Yes, sir.
I'm saying the time of nth arrival is less than or equal to 1. What does that mean?
Oh, within one,
Yeah, at least
say,
n people arrived, right? I'm not
yes,
saying,
sir.
it doesn't say that n plus 1th person didn't arrive within t, right? It doesn't say that. It's less than or equal to. So at least
Yeah,
n people arrived within a time interval of t. What is n of t?
enough the number of people
Number
survived
of people
at a time
arriving
t.
at time within an interval of t, right? So
Yeah,
it's greater than or equal to n. Both are equal, right?
yes, sir.
Hello, sir.
Yes.
Sir,
Yes,
from the
Rishabh.
first inequality, where Sn less than equal to t, sir, we can take the smallest possible value of t. Then, sir, no people can arrive. But from here, we deduce that n people arrived by Sn.
No. So it's not like that. So this event can happen, right? So even if you make t really, really small, still it's a very less chance, but that event can happen, right?
Yes, sir.
But this t is arbitrary. I'm not saying t is very small or large. Any t that you pick, these two are same, right?
Okay, sir.
Okay. So now, okay. So we have just to summarize, we looked at three things, right? One is Sn, the other one is Xn, and the third one is N of t, right? These three entities. So mostly we will deal with these two, okay? So because Sns are very complicated process, okay? So now let's look at how to model the arrival process, right? So there are different ways of modeling arrival process. So let's look at one of them, which is called the Poisson. Okay. we will try to understand what is Poisson arrival. Okay. So now towards this, let's first look at the definition of what is known as a renewal process. Okay. This is something that we will look at in some detail later on. And a renewal process is an arrival process okay, for which this I'll write and explain. Okay, for which if you look at the inter-arrival times, it's a sequence of IID random arrivals. Okay, inter-arrival times is a sequence of positive IID, positive IID random variables. Okay, so what do you mean by that? So it's like this. Okay, so what I'm going to do is randomly at some time I'll say tick. Okay, so I'll just put a tick mark here and I'll assume that there is one person arrived here. Okay, again when you do the same experiment again from here, it's independent of what happened in the past. Again I'll do a tick here and then I'll do a tick here, and see these inter arrivals, right? X1, X2, X3 and so on, these are IID. Okay, so now I'll define what is a Poisson process and then maybe stop. Okay, so a Poisson process is of course it's a renewal process. Okay, in which the inter-arrival times have an exponential CDF. Okay, the inter-arrival time have an, of course, since it's a renewal process, inter-arrival times are independent. So I have to say, I have to describe the distribution of one of those, not all of them. Okay, just have an exponential distribution with some rate lambda. Okay, so have distribution with some rate lambda. That is what we have. Okay, that is fx of x, that is your x is your inter-arrival time, is lambda e power lambda x greater than or equal to 0. This is what we have. Okay, lambda is called the rate because it turns out that the average number of people arriving per second is lambda. In t time interval, as for example, if you take a window of let's say t, the number of people arriving, average number of people arriving in this interval n of t is lambda t. Okay, it turns out. We will see why this is the case, but this is what it is, right? If x is exponential, so this is how I'm going to write in the future, exponential of lambda. This means it's distributed as exponential. Okay, then expected value of x is what? It's 0 to infinity lambda e power minus lambda x, of course x e power minus lambda x dx. So what is the answer? You have to integrate and see. So this turns out to be lambda. Okay, the average is lambda. Okay, so this lambda is called the rate of the process. Okay, is that fine?
Yes, sir.
So this integral is 1, right? Or
There is a
lambda
next
square,
man.
sorry. Lambda square, right?
No man, so there is an x, right? Expected value of x is what?
Yeah, expected value of x e power minus, integral x e power minus lambda x is lambda, right?
No, I don't think so.
Mean of x exponential random variable.
No, the exponential random variable is what? Lambda e power minus lambda x, right?
Oh, right,
Hey,
right, right.
just,
Yeah, yeah.
just
So,
integrate and see, man. So,
yeah, correct.
yeah. So by parts you can do it.
Yeah.
It'll be lambda. Okay. Is that fine?
Yes, sir.
Okay.
Sir, similar thing we have already done, I think, sir, for Bernoulli process, no, sir. There we
Exactly.
have got it
Right?
is, sir,
So
something
the Bernoulli
geometric.
process is a discrete. Yes, exactly.
Yeah,
So I'll come to that sometime later. Maybe you can go through it. So essentially, in Bernoulli, we didn't. So the inter-arrival times were independent, but it was not continuous, right?
yeah.
Yeah.
It was
So
discrete.
that is the difference.
Hello, sir.
Yes.
Sir,
Yes.
isn't
Yes.
it 1 by lambda?
Huh?
Yes, sir. 1 by lambda.
What is 1 by lambda?
E of
Expectation of x.
Yeah, I think so. Yeah, I think yeah, you are right. I think it's 1 by lambda. Yeah, right. Maybe. Yeah, please check this. Okay, I think it is 1 by lambda. Yeah, you are right. Thanks. Yeah, because yeah, you will have
Integral of
yeah.
1 by lambda square integral e power
Yeah,
minus.
so it will be 1 by lambda squared, and then yeah, true. You're right. So now I think okay. So now if it is 1 by lambda, so the average inter-arrival time is 1 by lambda. What does that mean? Right? What does that mean? So every 1 by lambda seconds, on an
Lambda
average,
means
there will be one arrival. Right? 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 Is that correct? So that means in 1 second there will be approximately lambda arrival. Okay, these are some sloppy arguments, but we'll make this rigorous later. So there will be lambda arrivals. In t seconds, how many will be there? There will be approximately lambda t arrivals. Right? This is how we get. So the average number of arrivals in t seconds is lambda t. Okay, so we get, if you take lambda as the answer, right, this integral, then you will get 1 by lambda t. That's not correct. So people, for example, they write this Poisson, the exponential. Some people write this same as 1 by lambda e power minus x by lambda. Okay. Some people write it like this also. So we will stick to this lambda e power minus lambda x. It's easy. Okay. Any questions so far? So because this is one of the interesting and very elementary, I wouldn't call it elementary, but very nice stochastic process to study. Okay.
So actually, sir, this distributions like this Poisson or geometric or it is exponential, sir. How do we get this kind of function? Is it a experimental or, sir?
Okay, so in many
Like,
cases,
sir, here
right?
we are taking the arrivals. We are just taking the random variables like Poisson processes, no, sir. And in there we have taken Bernoulli processes. So
Exactly.
how can we figure out what kind of?
It's actually a very good question. So there are two ways to, or two ways to think about it. Okay, one is, as you said, experimentation. Okay, so you figure out you stand at the, let's say, a circle and count the number of cars arriving from one of the ports per second, and you do the average and fit the distribution. Okay, that's one way. The second way is, for example, maybe I don't know if I'm not sure if I will discuss that here for Poisson, but for Gaussian, right, we saw there is something known as central limit theorem, right?
Yes, sir.
So irrespective of what x1, x2 are, right, it went to a distribution called Gaussian.
Yes,
right?
sir.
There it was
Yes,
very
sir.
natural, right?
Oh, yeah.
So it popped out of some rigorous mathematical argument, right? Even Poisson also, it turns out that it will pop out as a, you can make some rigorous argument about it. Okay, under certain, if you assume certain things about the process, then Poisson process is what you expect. Okay.
Okay, sir.
For example, this is one thing, right? My process. So if you increase your time, right? So one thing that you could have observed in your traffic, for example, if you look at one half an hour window, the average number of cars arriving is something. If you take 1 hour window, it's something. And if you take 2 hours window, it's something. If you plot all these three, okay, so these things, it will be something like this. So it fits a line with slope lambda. So, okay, that's something people would have observed. Then said, well, the average should be lambda t, right? And then they looked at a few other statistics and saw which distribution. How do I write this as a probability distribution? It turns out that it is Poisson. Poisson is one way of describing it. Okay. We will look at that very soon. Okay, these things, whatever I just mentioned, in a slightly rigorous fashion. Okay.
Okay, sir.
Yeah. Any other questions? Anyone else? Rishabh?
Hello, sir.
No? Nothing?
Hello.
Jayant?
No, sir.
Hello, sir.
No. Praveen? Nitish? Praveen?
No, sir.
No. Okay.
Hello.
Sumit? Anyway. Yes, Rishabh.
Sir, can you turn the page to the definition of renewal process? Sir, here you mentioned a sequence of positive IID random variables.
Yes. Yes.
So that
That's
means,
very important.
actually my connection lost that time. So, sir, positive IID means if a person comes, the next person should arrive after them, not before them.
Exactly, right? That's what we want, right? Naturally. Yeah. Exactly. So even if you consider that, I can remodel it saying, well, whoever arrived before me is the first one, right? So why do you want to? You understood, right?
Hello, sir.
Yes, sir, yes.
Yes.
So all the arrival process should be renewal process, right?
Not really.
No.
Hello. Can you hear me? Not really, right? Because you need IID. This is very important. Okay.
Otherwise, it will be positive, right?
Of course, you need positive. See, for example, if there is an arrival, okay, this is S1. Okay, let me call this as S1. S2 is this, then that means X1, this is 0, is this. X2 is minus of this thing, okay, whatever the length is, right? Now, if this is the process, why do you want to call this S2? You call this S1 and you call this S2, right? You agree?
Yes, sir.
Yeah. It's again a renewal process if they are independent. Okay. Okay.
But in which cases will they be dependent? The inter-arrival time.
Oh, very much right. So, for example, you look at the usual traffic. Inter-arrival time is highly correlated, right?
Or like you could think of if you're if you're thinking of packets in the internet, the first packet to ask a server to download a music file or something will come before the music file. So like I mean they're dependent kind of. You will get the music
Yeah,
file only if
that is also something. So one after the other, right? Is that did we answer your question?
Yes, sir.
Huh?
Yes, sir.
Jayant?
When the arrival of the next thing is dependent on the first thing.
Yeah, inter-arrival, okay. So not the arrival, inter-arrival time. Okay. So sometimes, you know, you ask your friend to go and stand in the queue and then you come, right? So your arrival, inter-arrival time. So let's say you go one after the other. Then also it's correlated, right? Inter-arrival time is correlated. You march next to your friend. So the inter-arrival time, he will arrive and then you will arrive. The inter-arrival time is highly correlated. In fact, deterministic, right? You almost arrive at the same time, except with some 4 seconds delay, let's say. Okay. It's like this, right? So I send 10 packets together, one after the other every 1 microseconds. And suddenly there is no packet to send, zero. Inter-arrival time is highly correlated in the first, and after that, you know, completely random, right? Random and non-IID, and also correlated because there is a burst of packet, with inter-arrival times being highly correlated. Okay, fine. Nitish, you had any questions?
No, sir.
If no, then we will we'll move on. Okay, so we'll stop here, and then in the next class we'll take up some. So please be prepared for the quiz. So what I'm going to do is, except whatever I discussed today will not be there for the quiz. Okay. Well, whatever I discussed, meaning Poisson thing. Okay, so till monotone, till dominated convergence theorem, we will have it for the quiz. But whatever I taught after that is not there for the quiz. Whatever I teach on Monday is not there for the quiz. Okay.
Okay.
Oh, yeah. Okay, so we'll meet on Monday. Monday, right? There's no class tomorrow. Yeah, Monday. Okay. Hey, Savan, just stay back. Others can leave if you want.
Okay.